This will be our last lesson of Unit 6, and it's going to cover percent yield. So we've already talked about theoretical yield. Theoretical yield is the maximum amount of product that can be formed based on our limiting reactant. So that means if everything goes perfect in the lab when we are doing this reaction, the theoretical yield is the maximum amount of product produced. Well, in theory, you're not going to produce that much. What you actually produce in the lab is going to be called the actual yield. The actual yield can be much lower, and that could be for a number of factors. Contamination, lab error. There could be a secondary reaction that produces different products. If your product isn't completely pure, that's going to affect the actual yield. So what we want to do is we are going to report our actual yield as what's called a percent yield. And the equation that we're going to use is the percent yield is equal to the actual yield divided by the theoretical yield, and then to get it to a percent, we're going to multiply by 100. So let's just start with a super easy calculation. If 3.2 grams of sodium sulfate were actually produced, but the theoretical yield was 3.6 grams, what is the percent yield? So for this one, all we have to do is plug this into our calculation and solve. 3.2 grams were actually produced, so the actual yield was 3.2 grams. If everything went perfect, theoretically we should have made 3.6 grams. And then we're going to multiply by 100. My masses have two significant figures, so 88.8 is going to round up 89%. The higher the percent yield without going over 100, the better. Alright, let's try one more problem, but for this one, I'm not going to give you the theoretical yield. I'm going to give you some lab data, and you're going to have to calculate both the theoretical and the actual yield. So let's say I had solid beryllium, and we reacted it with hydrochloric acid, which is an aqueous solution. That produces solid beryllium chloride and hydrogen gas. And then we're going to have a data table. Alright, so we're going to start with 1 gram of beryllium. 7.5 grams of HCl. And we're going to do this reaction in an Erlenmeyer flask. Before we do the reaction, I'm going to record the mass of the empty flask. Let's say it is 109.4 grams. And then we're going to do this reaction. So into the empty Erlenmeyer flask, I'm going to add beryllium and hydrochloric acid, and it's going to produce these two products. Hydrogen is a gas, so we're going to see that the reaction is going to start to bubble, and then the gas is going to get released into the air. That means we're going to be left over with just solid beryllium chloride. So then we can take a final mass, which would be the mass of the flask plus beryllium chloride. Let's say that was 116.7 grams. We're going to have a series of questions to answer based on this reaction and this data. First, we need to determine the theoretical yield of beryllium chloride. So even though this is in terms of a data table rather than a question, it's going to be just like our limiting and excess reactants. I have a starting amount of beryllium, and I can solve for grams of beryllium chloride. I also have grams of hydrochloric acid, and again, solving for beryllium chloride. I have 2 givens. I need to do 2 calculations. So let's start with the 1 gram of beryllium. If we're starting with grams, the only thing we can do is plug in molar mass to get to moles. I can look up beryllium on the periodic table. It has a molar mass 9.01 grams per every 1 mole. We are solving for beryllium chloride. Given beryllium, I have 2 different substances, so I need a mole ratio. 1 mole of beryllium can produce 1 mole beryllium chloride. Lastly, when we're looking for theoretical yield, we're looking for grams. We need a mass. So I can quickly calculate that. Chlorine has a mass of 35.45, and there's 2 of them, plus the mass of beryllium that we looked up, 79.99. Again, you should already know how to do these calculations. This is like the 4th lesson that we've done these 3-step calculations. So now let's grab a calculator and solve. 1 times 1 times 1 times 79.91 divided by 9.01 times 1 times 1, 8.869. My given has 2 significant figures. My answer can have 2 significant figures. I'm going to round this up to 8.9 grams. For these limiting reactant types of problems, we have 2 givens. You have to do 2 calculations. So let's do the same thing, starting with 7.5 grams of hydrochloric acid. If I'm starting with grams, the only thing I can do is plug in molar mass to get to moles. Now I'm at moles of hydrochloric acid, but I'm solving for the yield of beryllium chloride. I have one substance, I'm solving for a second substance, so I need the mole ratio. 2 moles of HCl can produce 1 mole BeCl2. The last step is always the same because I'm solving for the same thing. I'm at moles of beryllium chloride. I need to get to grams, so I'm going to plug in its molar mass. All right, let's solve this one. So again, if you're doing one big calculation, put everything in the numerator in parentheses and then divide by everything in the denominator in parentheses. So 7.5 times 1 times 1 times 79.91. So the whole numerator goes in parentheses, divided by, and then put the whole denominator in parentheses. 36.46 times 2 times 1, and your parenthesis. My given has 2 significant figures. Round my answer to 2 significant figures, 8.2 grams. Again, you cannot leave your answer like this because I don't know which one of these is the theoretical yield. So find a way to tell me which one is which. Remember, the theoretical yield is always the smallest yield of product. So your answer would be 8.2 grams. The other thing that I want to point out is the theoretical yield is not whichever reactant you have less of. Sometimes students say like, well, I have less beryllium, so that means I can make less product. That is not the case. I actually have more HCl, but I can make less product. So it has to do with their molar masses and also the mole ratio. So don't think just because I have less beryllium, that's automatically going to be the limiting reactant. It doesn't matter on the amount of reactant, it has to do with the amount of product produced. HCl makes less product, that means it's limiting. All right, few more follow-up questions. So we have our theoretical yield. You might also be asked to determine your limiting and excess reactants. So the limiting reactant makes less product. HCl made 8.2. Beryllium made 8.9 grams. HCl made less, so it's limiting. That means the excess reactant is beryllium. After we made 8.2 grams of product, we would still have some beryllium left over. C. Calculate the actual yield of beryllium chloride. So to do this, we have to go back to our data table. So I have the mass of the empty Erlenmeyer flask, and I have the mass of the flask plus the beryllium chloride. I want to know what is just the mass of the beryllium chloride that we made in the lab. So what we can do is if we take the mass of the flask plus beryllium chloride and you subtract out the mass of just the flask, that would give you the mass of our product. So the mass of the flask plus our product was 116.7 grams. If I subtract out the mass of just the flask, that would tell me how much beryllium chloride we have. .3 grams. Remember, with significant figures, when you're adding or subtracting, we round it to the least number of decimal places. 1 decimal place, 1 decimal place, so our answer has 1 decimal place. We actually produced 7.3 grams. Lastly, calculate the percent yield. So again, the equation, actual divided by theoretical times 100. The actual yield, 7.3 grams. Back in question A, our theoretical yield, 8.2 grams. So theoretically, if everything went perfect, we should have made 8.2 grams. In reality, we actually made 7.3 grams. So we can now calculate our percent yield. 7.3 divided by 8.2. And then to get that to percent form, we can multiply by 100. My masses have 2 significant figures. My percent yield has 2 significant figures, 89%. The higher the percent yield, the better. So 89% is a pretty good percent yield.